Hi, and welcome to Dr. V's Chemistry Webcast. In this webcast, we're going to discuss limiting reagent problems. Limiting reagent problems are an important real-world application of chemistry and a very important application of stoichiometry. What I'd like to do in this webcast is to use particle-level diagrams to introduce and explain the concept of the limiting reagent and show you how to recognize limiting reagent problems. If you don't realize it's a limiting reagent problems, you won't treat it properly. And then I'd like to introduce a strategy we can use to solve limiting reagent problems that's very reliable and very predictable. And of course, we're going to work through a complete practice problem. Particle level models are actually a really good way to introduce this idea. Let's say we have a reaction between A2 molecules and B atoms to make AB2 molecules. And here's the balanced equation. Let's say that before the reaction, we start with 3 molecules of A2 in our reaction vessel. And we have 8 atoms of B present as well. And then we're going to let them react. So we know for the product, 1 atom of A ends up with 2 atoms of B. So as the reaction proceeds, we start making AB2 molecules. And it keeps going. But what we find before too long is that all 8 atoms of B have reacted, but I haven't reacted all of my A2 molecules. I was only able to make 4 AB2 molecules before I ran out of B atoms, meaning I have 1 molecule of A2 left over. So I ran out of B, and therefore I can't make any more products. And this is really the idea of the limiting reagent. I had to stop making products because I ran out of one of my ingredients. In a real-world situation, we don't always put our reactants together in exactly the right proportions. We often have one reactant that runs out first. We call this the limiting reagent. And because we've run out of this, the reaction has to stop, and we can't make any more product. It's sometimes referred to as limiting reactant. Limiting reagent, limiting reactant, these terms are interchangeable. In the picture models that we were looking at, B was limiting reactant. I ran out of it first, and therefore I couldn't make any more AB2 molecules for the product. Meanwhile, the other reactant is left over. This reactant is in excess because we didn't use it all up, and it's still there when we're done. In our particle level model, A2 was in excess. We had 1 molecule of A2 left over at the end when we had used up all of B. In a real world situation, we might have 1 reactant that's really expensive or very difficult to acquire. You don't want to waste that, so you're going to have that be limiting, and the other reactant could be in excess because if you waste the inexpensive one, well, economically that just makes more sense. It's actually very rare to put things together in exactly the right proportions based on the stoichiometry of the reaction. So how do you know it's a limiting reactant situation? Well, the easiest way to tell this when you're doing a problem set is that you're given the amounts of 2 or more starting materials. You have initial masses of both reactants or all the reactants in the reaction. And that's your clue that it's a limiting reagent situation. In fact, it might be your only clue. You might be asked what's the limiting reagent. You might be asked how much of the excess reagent remains at the end of the reaction, but you might not. Either way, you need to know it's a limiting reagent situation so that you can then solve the problem appropriately. If you're doing a problem on a particle level basis or even on a mole basis, you can actually draw the numbers and kinds of product particles that you can make from those starting materials. But when you're doing a problem on a mass basis, you've got a real world situation and you've got masses of all your reactants, that's really not going to be a viable approach. We need a way to solve limiting reagent problems when we're starting with masses of both reactants. There are 4 or 5 different ways to solve limiting reagent problems. I'm going to outline the strategy I like to use myself because I think it's the most straightforward of the different strategies and doesn't require a new approach. It does, however, assume that you're very comfortable solving stoichiometry problems using dimensional analysis. What I like to do is to calculate the amount of the product that I'm interested, how much of that would be formed if the first reactant were completely consumed. And then I'm going to calculate the amount of that same product, how much would form, if the second reactant were completely consumed. And if you had a third reactant and you knew its quantity to start with, you do that calculation too. Once you've got these 2 calculations, then you compare them. Whichever calculation gave you the smaller calculated amount of product gives you the theoretical yield for that situation. Whatever reactant was involved in the calculation that gave you the smaller value will be your limiting reactant, and the other reactant is in excess. Any other stoichiometry calculations that you need to do need to be based on the limiting reagent. I like this strategy because I don't need to remember another set of rules. I just do the calculations I always do, and I do them twice. All of the strategies for limiting reagent problems involve multiple calculations. Let's put our strategy into play and solve a problem. When zinc sulfide is heated in oxygen, zinc oxide and sulfur dioxide gas are produced according to the chemical equation here. If 18.2 grams of zinc sulfide and 29.7 grams of oxygen react, what mass of zinc oxide will be produced? Now you should be saying to yourself, oh, wait a minute, I've got the masses of both reactants. This must be a limiting reagent problem. And you're right, it is. They don't always come, though, on worksheets or in webcasts that tell you, hey, this is a limiting reagent problem. You need to recognize that. And just for an extra layer of complexity, we're going to also ask what mass of excess reagent will remain at the end of the reaction. We've got our balanced equation. Of course, you always need a balanced equation to do any stoichiometry problem. We know we have 18 grams of zinc sulfide initially and 29.7 grams of oxygen initially. We want to know the mass of zinc oxide that will form. That's what the question asks us to do. We need to do the two calculations. What mass of zinc oxide would I get if 18.2 grams of zinc sulfide reacted completely? Let's do that calculation now. I'm going to take my grams of zinc sulfide and turn it into moles of zinc sulfide. I'll then use my mole to mole ratio to get moles of zinc oxide, and then I'll use the molar mass of zinc oxide, and I get an answer, 15.2 grams of zinc oxide. But I can't assume that I'm done here. I haven't done the other calculation, and until I do that other calculation, I don't have enough information to answer the question. I need to know what mass of zinc oxide would form if all 29.7 grams of oxygen reacted completely, and I need to do this calculation. So I'll take my grams of oxygen and convert it to moles. I'll use my mole to mole ratio to get moles of zinc oxide, and I'll use the molar mass of zinc oxide, and I get a value. I get 50.4 grams of zinc oxide. So now I've got the two calculations, and I can compare them. What's smaller, the answer from the first calculation or the answer from the second calculation? Well, it's really clear that 15.2 grams is smaller than 50.4 grams, and therefore I can conclude that the theoretical yield of this reaction is 15.2 grams of zinc oxide. That's the maximum amount of zinc oxide I will get. Because zinc sulfide is the reactant for that calculation that it was based on, I can state confidently that zinc sulfide must be the limiting reagent and oxygen must be in excess. And I can say that I must have run out of zinc sulfide first because I made less zinc oxide. If I had run out of oxygen first, that calculation would have given me the lower mass of product. We had also wondered what mass of excess reagent will remain. We found on the previous slide that zinc sulfide was the limiting reagent and that oxygen was in excess. So we need to figure out how much oxygen was left over. Well, I know how much I started with. If I want to know how much is left over, I need to know how much got used. That's the next calculation I need to do. What mass of oxygen was consumed when all 18.2 grams of zinc sulfide reacted completely? So I'm going to convert my grams of zinc sulfide to moles. I'll use my mole to mole ratio to find moles of oxygen, and then I'll multiply by the molar mass of oxygen, and I get a mass of 8.96 grams of oxygen that were consumed. I started, though, with 29.7 grams. This does make sense. I didn't use all of my oxygen. We know oxygen was in excess, and in fact, I used only about a third of it. Since I started with 29.7 grams of oxygen initially, and I used 8.96 grams, I can say that 20.7 grams of oxygen will remain after the reaction is complete. These are higher level extensions of limiting reagent problems, but I really think students can do these. You have to think about your strategy and make sure you're solving the problem in a way that makes sense and that your work supports your answer. A lot of everyday situations actually involve stoichiometry and limiting reagent applications. If you run out of eggs, you're going to stop making cookies. In chemistry, we use this a lot, and you need to recognize that you have a limiting reagent situation and have a strategy that supports your answer and that makes sense and is reasonable. I hope you found this helpful. Subscribe to my channel so you hear about all my latest videos. Like the video and leave a comment. Make sure you study chemistry every day. That's the road to success.